Hello and welcome. Today's webinar is Data-Driven Mobility Strategies for Multimodal Transportation. My name is Brendan Williams. I'm the Research Program Administrator at Portland State University's Transportation Research and Education Center. TREC leads the National Institute for Transportation and Communities, a university transportation center funded by the U.S. Department of Transportation. NITC consortium members are the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and Oregon Institute of Technology. NITC's research priority is improving mobility of people and goods to build strong communities. Our presenters today are Yaoyan Wu and Abulfazl Karimpour from the University of Arizona, and Xiangfeng Terry Yang and Kuizhang Wang from the University of Utah. Also Shirisha Kothuri from Portland State University. Our next NITC webinar is on October 12th from 10 to 11 a.m. Pacific time. It's on the impact of transportation-related barriers on self-perceived physical health among adults in the US. It's presented by Philip Biden and Godfrey Boateng from the University of Texas at Arlington. The presentation is going to be about 40 minutes long, and then we're going to have about 15 minutes to answer your questions. During the presentation, please submit your questions in the Q&A. That'll help us just keep a structure to it. If we get them all in at the end, it's going to be a little bit chaotic, but we're going to try and handle them as best as we can. There's about 150 attendees here, so if you really want to ask a question, the sooner the better. After the webinar, you'll receive an email with the link to the video recording and the presentation slides. If you're tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. Instructions on how to redeem the credit will be included on your post-webinar email. And with that, I'm going to turn it over to our presenters. So Abulfazl, if you'd like to take over, great.
Okay, thank you everyone. Thank Brendan and I'd like to thank NITC for this opportunity to give us opportunity to talk about this project. I'm the PI of this project. My name is Yao. I think I'm here also want to appreciate, say thank you to my team members. Abulfazl was a student actually working on the project. He did all the work, so that's why he'll be talking most of the work today. I would like to thank Dr. Xiangfeng Yan, Terry Yan. He also lead his team at Utah in Utah, and also last one, Shirisha, Dr. Shirisha Kothuri, and Jason actually also on our team too. They help us a lot with the project. I really appreciate the team's help, and our team actually meet regularly in the project. It was a really fun project. I'm glad we can share some results with you. Next slide, please, Abel. So this today's agenda, we have a lot of things to cover. And if you guys remember, the topic is actually quite broad, but I like everyone to focus more on the data-driven, this keyword, data-driven mobility. So what we're gonna do is Abulfazl is gonna give an introduction. We're gonna talk about what our approaches are for convention corridors. And then Dr. Yan's team gonna talk about the connected corridors. And then Abulfazl and Shirisha will talk about multimodal transportation. And we'll summarize this presentation with the key learning and the broader impacts. Basically, take away, we made a lot of effort for this project. We want somebody like you guys to learn from what we have learned too. Next slide, please. So when we start developing the idea for the project, we thought about everything really big. Okay, so it's multimodal mobility strategies. I know this topic sounds like a multiple PhD dissertations. It's right, it's a lot of topics we could cover in this general topic. So our team further narrowed down to two corridors. two types of corridors. One is called a conventional corridor, the other is connectivity corridor. Basically, conventional corridor is basically we try to use the existing data infrastructure, traffic sensor infrastructure to collect data to see how can we improve traffic better. Multimodal in this case actually will not only look at the vehicular traffic, we also look at pedestrian traffic. So that's the two things we focus on in this study. And Dr. Shenfeng Yan's team, they focus on more advanced corridors, which is connected corridors. So in Utah, they actually have advanced devices installed on a study corridor. They were able to do something beyond what we have right now. So one is more futuristic, one is more current. I thought this project was fun because it actually cover current status and future status to make sure we can achieve the goal of smart city. Next slide, please. So these are the three major objectives for the study. As I mentioned, the topic of the study, this project is kind of broad. So to make sure we can use our limited resources to finish the whole project, we focus on three things. First thing is the impact of speed management strategies on conventional roadways. That's why I just mentioned with the data-driven approaches to solve some speed management issues. Second one is the connected corridor issues done by Utah's team. The third one is pedestrian delay at signal intersection. Basically, we use some existing sensors to grab some new data, and these data are actually available in the, using the current the sensor we have in the field. So we did some interesting study to collect some pedestrian delay information. Anyway, so without further ado, I'd like to turn this to Abulfaz. He actually the main researcher of this project. He actually helped me coordinate a lot of things among the team. So I'm gonna turn this to Abulfaz to explain our effort. Abul?
Thank you, Dr. Wu. Thank you everyone for attending this session. Before I start, I would like to thank and acknowledge some members, Utah Department of Transportation, NITC, and Pima County Departments of Transportation for supporting this project as well. Perfect. So let me start with conventional corridors. As Dr. Wu mentioned, we focused on two different corridors, conventional corridors and connected corridors. For the conventional corridors, we focused on speed management strategies, or the impact of speed management strategies on the mobility of the corridor and on the intersection performance measures. Now let me talk a little bit about what are the primary outcomes of an effective speed management strategies. Speed management strategies are aimed to improve mobility and vehicle progression by reducing the non-recurrent delays and reducing incident-induced delay. Also, they will improve the public health by reducing the speeding, by reducing the number of vehicles which are speeding. What are some of these speed management strategies? One of these speed management strategies that everyone are familiar with are speed tables, rumble strips, and speed humps. There was a lot of studies that concentrated on these type of speed management strategies, and they showed these speed management strategies are effective. However, we are not able to implement all these type of speed management strategies on different roadways. For example, in a high-speed roadways such as our study corridors, we are not able to implement a speed table. The other things that we looked at was speed feedback signs. Speed feedback signs are these signs that once you pass them or you are approaching them, they will show your speed. As you can see in this picture, when you are passing this sign, there is an electric sign that will show you your speed is, and also they have the speed limit under it. There has been some studies, implementation of speed feedback signs in school zones, work zones, transition areas, and urban and rural roads. And most of these studies showed that how speed feedback signs are able to reduce the speed by different percentage. However, one problem with the speed feedback signs that we encounter in our project, in our study, we find out that these speed feedback signs, people or drivers only reduce their speeds when they are close to these speed feedback signs. And also we wanted to understand whether these speed feedback signs will impact the intersection performance measure. The other speed management strategies that we looked into was law enforcement. There has been a lot of studies showing that law enforcement will reduce the aggressive and risky driving. They will target fatal crashes, and also they will increase the seatbelt usage. However, again, based on the DOT or based on the city, not always enough resources are available to enforce all the roads. Therefore, we need to figure out what type of strategies, how we can use these strategies effectively to enforce speed on conventional corridors. So here is a summary. As I mentioned, roadway designs are not always applicable. As I mentioned, we are not always able to put them in high-speed roads. Continuous enforcement is costly. Not all the DOTs, cities have enough resources to enforce all their roadways. Speed feedback signs, drivers only reduce their speed at the vicinity of these signs, so they are not always the best approach. And also some of you might have these questions, okay, why not just use speed enforcement cameras? As you know, speed enforcement cameras are not legal in all states. One of these states is Arizona. We are not able to use speed enforcement cameras in our state. Therefore, this study was built to see what other strategies can we use, how we can take the advantages of the current studies, and how they will impact speeding and signalized performance at intersections. First, let me talk a little bit about the impact of speed feedback signs on the intersection performance measures. In order to conduct this study, we look at 4 segments in Pima County, Aina Road, and we identified some locations with active speed feedback signs and sensors installed at the intersection. For the first part, I will talk about how speed feedback signs will impact the performance of the intersection. As you can see, I have 4 segments here. In order to conduct this study, we activate these speed feedback signs for a specific amount of time, which was 2 weeks for our study. Then we disabled these speed feedback signs, and then we reactivated the speed feedback signs. And during these procedures, we looked at how signal performance measures such as intersection delay, arrival on red, split failure might change after enabling and disabling speed feedback signs. In order to conduct that, we collected 5 different data: vehicle volume, delay, arrival on red, split failure, and speed. All these data were collected from the study corridor that we selected for all of those 4 segments. In order to make sure that during our procedures after enabling speed feedback signs and disabling speed feedback signs, whether we have a difference in volume or not, we quickly look at the volume difference for all those segments. Here, I just included one of those segments, eastbound from North Shannon all the way to La Cholla Boulevard. As we dig into the data, based on the statistical analysis that we did, we found out that volume did not change during our study corridor. So for that part, we are good. Now we will look at how speed feedback signs, enabling speed feedback signs might impact the intersection performance measure. The first measures that we looked at was arrival on red. In order to understand this, we collected data arrival on red on those study corridors before turning speed feedback signs on and after turning speed feedback signs on. So if you look at this table, you will see that I have an average for on and I have an average for off. So based on this, the statistical analysis that we developed, we understand that for neither of the time periods, AM peak, PM peak, or off peak, the mean or variance of arrival on red did not change after enabling the speed feedback signs. So in conclusion, at significance level of 0.05, there is no sufficient evidence to reject the null hypothesis. What was the null hypothesis? The null hypothesis was that arrival on red before and after enabling speed feedback signs is the same. So we conclude that the operation of speed feedback signs does not have a statistically significant impact on the percentage of arrival on red. We did similar studies for other measures. As I mentioned, we did this for delay and we did this for split failure. However, based on the study analysis, based on the statistical analysis that we conducted, we find out that speed feedback signs, enabling speed feedback signs on our study corridor, on that conventional corridor, does not impact neither of intersection performance measures. So in conclusion, we can say that speed feedback signs does not have any statistical significant impact on signal performance measure. However, the next question of this study was how to improve the effectiveness of speed feedback signs. As I mentioned earlier, speed feedback signs has an issue. Drivers only reduce their speed at the vicinity of these speed feedback signs. So we wanted to know how we can solve this issue, because Arizona, we are not able to use a speed camera. So what can we do? We came up with this idea. What if we mix and match speed feedback signs with law enforcement? And instead of using law enforcement for all the time period, let's use law enforcement, periodic law enforcement. Periodic law enforcement means that we talk with the sheriff department, we ask them, please show up at these locations that we identified for you in certain point of time, in the certain data collection. For example, if we had 1 week of data collection, we ask the sheriff, we ask the lieutenant to show up randomly on these locations. So in order to understand this, we set up this study experiment. We selected 3 sites with only speed feedback signs, no law enforcement. Then we selected 3 sites with periodic law enforcement. And finally, we selected 3 sites with periodic law enforcement plus speed feedback signs. In order to understand how these different sites, how drivers behave in these different sites, we collected data at 3 locations. This data collection design is similar for all those 9 sites. We collected data at 3 points. 1 point, we call it baseline data collection. This location was on upstream of speed management strategies. For this study, the speed management strategies, again, are speed feedback sign only, periodic law enforcement only, and periodic law enforcement plus a speed feedback sign. The second location that we collected data was by the speed management strategies. And finally, we collected data downstream of speed management strategies. We put this location to find out whether the drivers will regain their speed after passing these speed management strategies, or they will keep their speed low. The results was very interesting based on what we observed. So I'm just going to talk about the results for 1 site, speed feedback sign only, periodic law enforcement only, and periodic law enforcement plus a speed feedback sign. The first location that I want to talk about is a location where we have both speed feedback signs and periodic law enforcement. This is the first location where we collected data, baseline data collection. The average of speed for this location was 47.5 miles per hour. The second location that we collected data was in the vicinity of speed management strategies. The average speed that we observed here was 45.6. And finally, after passing the speed management location, we collected the speed again, 42.7. It is important to mention that these data are for 1 week of data collection. So we had more than 1 million point of data, and this is just the average of them. So we can understand that we can do a statistical test to see whether this reduction was statistically significant or not. For this case, as you can see, we had almost 2 miles per hour reduced in speed, which this reduction was statistically significant. Going from this location to this location, again, we saw almost 3 miles per hour reduction of the speed, which was again statistically significant. Now let's go to the other location. This location, the speed management strategy installed there was periodic law enforcement. This is the first location, baseline data collection. This location is a location that the vehicles were not aware of that specific speed management strategies. So the drivers had no idea there was a police standing there or there was a speed feedback sign there. The average speed for here was 48 miles per hour. And at the location where drivers saw the police car or where drivers see the speed feedback sign, they reduced their speed by 45 miles. The average speed reduced to 45.6 miles per hour. And then after passing this location, which was downstream of data collection, you can see that drivers regained their speed by almost 1 mile per hour. So based on this, you will see that drivers only reduce their speed in the vicinity of periodic law enforcement. Now let's look at the other strategy, which was a speed feedback sign only. Again, we collected data at 3 locations. Before the drivers were aware of speed management strategies, they were going with 43 miles per hour. When they saw the speed feedback signs, they reduced their speed by 42 miles per hour. And then after passing a speed management, which for this case was a speed feedback signs, they regained their speed and their speed increased by almost 1 mile per hour. Some points that I need to brought up here is that from going from this location to this location, we selected this in a way that if the drivers want to speed up, they have the opportunity. So they had the opportunity to speed up. But for this type of speed management strategies, the drivers did not speed up. However, for periodic law enforcement and a speed feedback sign only, the drivers regained their speed after passing the enforcement. So in conclusion, based on this, based on the first section of this study, we identified a key speed management strategies. These key speed management strategies was combining speed feedback signs with periodic law enforcement, which will increase the spatial effectiveness of the speed feedback sign and will not have any impact on the intersection performance measure. The result or the conclusion of this study, DOTs that are looking to expand their speed feedback signs coverage can take advantages of these results and can use their this methodology for their roadways. And finally, coordinated efforts between transportation agencies and law enforcement will help to address the speeding issues, which I mentioned. There are so many different speed management strategies. However, looking at individual of them, we are not able to solve all the speeding issues. So with this study on the conventional roads, we find out that if we combine speed feedback signs with periodic law enforcement, not only we are able to reduce the speeding at arterials, but also this strategy will not have any impact on intersection performance measures, and it's not as costly as putting a police car or a sheriff all the time at one location. With that, I would like to ask University of Utah to talk about their strategies, speed management strategies for connected corridors.
Okay, thanks Albo's presentation. Albo, can I share my screen to on my end? Okay, thanks. This is Chinzhen Wang from the University of Utah. Next, I will introduce the effect of TSP on connected corridors. I'm so sorry I didn't put one slide to introduce the basic condition of the connected corridor. So I will describe briefly before going through the following slides. Over the past decade, dozens of civil test beds were built in US, and a test showed that great potential of civil technology on improving traffic efficiency. So UDOT built a full DSRC corridor for civil technology testing on November 2017. This corridor is located along Railroad Road in Salt Lake City, and it's 11 miles long and includes about 30 signalized intersections. Currently, this corridor is used for supporting TSP when vehicle comes in, when the bus comes into the communication range. The V2I function will collect the bus information, and TSP functions will be activated if the bus is behind its scheduled time for certain criteria. As we all know, TSP has many benefits such as bus delay reduction, bus reliability improvement, but it can also bring negative impacts on intersection traffic due to the changing signal timings. So the UDOT tries to change the signal timing plan to get a better performance. So this project aims to evaluate the system performance before and after signal timing in October 2017 based on the collected data. So, and the data we collected is in August, September, November, and December in 2018. And they are from three main sources: DSRC data, ATS-PM data, and UTA data. DSRC data is generated when messages are transmitted between OBU and RSU. It includes BSM, SRM, SSM, and map shown in this figure. Oh, this showed map message. And BSM data is the information about the real-time operation status of the bus, including location, speed, heading, so on and so forth. And SRM data is about the information that's sent by bus to request TSP service. SSM data is about the information of the reply to the TSP request, and map data is about the information of the intersection geometry. The ATS-PM data is collected from the signal controller. It includes signal ID, TSP request activations and consignations, so on and so forth. And the UTA data is collected from Utah Transit Authority, and it's all about the bus travel information such as bus ID, direction, schedule time, so on and so forth. Based on those data, we can calculate travel time, operation time, and bus reliability, and the TSP served ratio and the request ratio. But before doing this, we need to process the data firstly. Let's look at the BSM data first. This is a sample of the BSM data, and the time step in this database is in GMT style. We need to transfer it to MST, and the heading column is used to determine the direction of buses, and the bus line along this corridor have 4 directions. Because this project focuses on northbound and southbound, so we need to remove the eastbound and westbound direction. For the summertime, we transfer the GMT to MST using this equation, and during the wintertime, we use this equation. We use a simple method to define the 4 directions I show in this slide, and then we remove the eastbound direction and westbound direction. This is a sample data of SLRM data, and in the same way, we need to transfer the time step and filter the direction. Because we want to know the TSP request ratio and served ratio, because TSP served ratio is according to ATS-PM data. So or the date in the SRM database need to be same as the date in ATS and PM database. And this is the sample data of ATS PM data. Like I said before, the data in the ATS PM database need to be same as the data in SRM database. Because there are two types of controllers along this corridor, and ATS PM database use the event code to determine if the TSP is served, and the event code is related to the controller type. So we need to add the controller type for each single ID. And this slide shows how to process the ATS PM data. And this is a sample of UTA data, because this column shows that there are 5 status of the bus according to UTA. They are on time, critical or late, critical late, and we need to filter on time to calculate the reliability. Besides, we need to split the directions into northbound and southbound for analysis respectively. Based on the field data, now we can select 18 intersections along this corridor for case study. This table shows the metrics we can get for each database. From BSM data, we can count the number of buses that drive across a certain intersection, and for SRM data, we can count the TSP requested TSP numbers, and from the ATS PM data, we could know how many requested TSP are served, and the UTA data we could know the information about the bus traveling along this corridor. Next, let's look at the result in detail. First, let's look at the reliability. We calculate the reliability by adding up all on-time arrivals and then divided it by the total arrivals at each station. And according to the UTA, a bus is considered on time when it's less than 5 minutes behind its scheduled arrival time. And this figure shows the bus reliability before and after signal retiming, and the blue bars shows the reliability before signal retiming, and the orange bars show the bus reliability after signal retiming. We can see that the reliability for northbound and southbound all improve after signal retiming. This may because after signal retiming, the TSP served ratio improved, so it can cause more late status to on-time status. And this slide shows the travel time and operation time of buses along this corridor. The travel time means the time that the bus travel from the departure station to the terminal station, and the operation time equals to travel time minus dwell time. And these two figures show the result, and the blue bars shows the travel time or operation time before signal retiming, and the orange bars shows the travel time and operation time after signal retiming. We can see that after signal retiming, the travel time and operation time can reduce. Besides the different dwell time, the main reason for this is also because of improved TSP served ratio, and it can cause less stopping when bus travel across the intersection. To better know how this system operates, we need to know how how many requested TSP are observed are served. So these two figures shows the TSP requested ratio and TSP served ratio before signal timing and after signal timing. And the yellow areas represents the request ratio, and the blue arrows represent the served ratio. And we can calculate that the average ratio of TSP served to before signal timing is 33.13%, and the average percent of TSP served ratio after signal timing is 35.29%. We can notice that actually the bus served ratio, bus TSP served ratio is low. This is because many requests requested TSP, the bus can travel across the intersection during the green time. So this TSP request will be cancelled. In conclusion, the TSP supported by CV technology can improve the bus reliability, and if we design a better signal timing plan, and the bus reliability, bus travel time, and operation time can improve better. Okay, thanks. Next for the other part.
Thank you, Shejan. Thank you for your presentation. Now I will dig into the multimodal part of this presentation. For this part, we dig into pedestrian delay. What are the measures? What are the ways that we can estimate pedestrian delay at signalized intersection? But the main question is, why is it important to understand the pedestrian delay? Why is it important to estimate pedestrian delay? The first thing is that pedestrian, as you all know, you have this experience in your daily life. Pedestrian level of frustration grows when increase of pedestrian delay. So if I'm standing still in an intersection, I don't get a green light. When there is no vehicles coming, I tend to pass the intersection. So we have to make sure that our signalized intersection are developed in a way that we can also see pedestrian safety. The second reason would be delay in general is one of the most significant signal performance measures. Most studies has concentrated on vehicular delay. However, it is also important to look at the more vulnerable road use, such as pedestrians. What are the delays that they are experiencing in their daily use? As you all know, delays will quantify the operation level of service at intersection. So either vehicular delay or pedestrian delay. And finally, pedestrian delays affects pedestrian disproportionality when compared to other users. Mostly for most DOTs or for most cities, they mostly concentrate on vehicular delay. However, it is very important to make sure that the delay that are impacted to the pedestrian is proportional to the delay of other road users. So in order to understand these measures, in order to understand the delay of pedestrian, we developed these measures to estimate pedestrian delay at signalized intersection. However, it is very, however, we wanted to know how we can do this approach using the available sensors installed on the city. To do that, we selected 4 intersections, again on Aina Road, Pima County, and used the available sensors where it was smart sensors to collect high resolution event-based data. The data that we collected from these intersections were cycle length, traffic flow, pedestrian delay, and pedestrian green time. And we tried, we proposed this approach to estimate pedestrian delay. So the first step that we did was we identified some of these variables, such as cycle length, traffic flow, that can best characterize pedestrian delay distribution. Then we developed a finite mixture modeling approach to use these measures, as I mentioned here, these data that we collected to model pedestrian delay. And finally, we evaluated whether the proposed method for pedestrian estimation is also transferable to the other intersections. So maybe not all the intersections in Pima County or not all the intersections in Utah are equipped with these type of sensors. So what can we do? If we have these variables, for example, cycle length, traffic flow, are we able to use this proposed method to estimate the pedestrian delay? We will answer this question in this study as well. So I won't talk about the modeling, the formula, the approach that we use. I jump straight into the results. As you all know, there are several well-known pedestrian estimation models. One of them is HCM 2010 and HCM 6th edition, which I have the formula here. The other methods, which are a little bit older, are Wickler methods and Dunn methods. So in order to understand that where does our proposed model stands, we compared our model with several of these well-known models. As I mentioned, we had 4 intersections. So I developed the delay per time of the day for each of these intersections and compared them with these additional methods. The actual is the actual delay, and this line is the proposed method. Looking at these figures individually, you will understand that the proposed method, the approach that we are proposing, we are able to capture all the fluctuation of pedestrian delay during the day. For example, if you look at this point, there was an increase in the pedestrian delay. Our method was much more accurate than the other 2 methods. Or look at this intersection. There is a drop in pedestrian delay at this location, 1 p.m. Looking at this method, looking at the proposed method, you will see that we are able to clearly capture these spikes. So the second conclusion would be the proposed method is robust toward the spikes happening during the day. So comparing this proposed method with other conventional methods, you will see that the proposed method is superior or in both accuracy, and it's more robust toward the fluctuation of pedestrian delay during the day. The second thing that I want to talk about is whether we are able to transfer, whether we are able to use this model in other intersections. So we did a quick transferability test for this purpose. Why? Calibrating estimation model is usually costly, complex, and time-consuming procedure. Second, as I mentioned, it is not always feasible for agencies to collect sufficient traffic data at each individual intersections to perform this modeling procedure. So what we did here is that we trained some models, 4 models with 1 single intersection, and then we predicted the pedestrian delay at the other intersection in order to understand that whether the model developed for 1 intersection is also able to estimate or predict the pedestrian delay at other locations. The number here is RMSE per second for the proposed model, and the one in the parentheses, we just use HCM 6th edition method. So you can see that for this specific location, let's take this intersection as an example. If I develop a model, pedestrian estimation model for this intersection and predict the pedestrian estimation for the other intersection using the proposed method, I can get pedestrian delay with 17 seconds error, RMSE. However, if I use HCM method, I will get 40 seconds of delay. And similarly for the other intersections, the other transferable models, you can see similar results. So looking at these results, you will understand that the proposed method is also able to predict other intersections delay as well. We did this for 4 intersection, train it and test it on 4 other intersections. So what are the application of this research or this method? First of all, we proposed a more reliable, robust, and accurate approach for estimating pedestrian delay at signalized intersection. Second, based on this approach, based on this modeling, we were able to develop pedestrian delay density function at each intersection. This pedestrian delay density function can help for analyzing the risk of pedestrian violating the signals. Why this can help? Because if you look at the pedestrian delay distribution at the locations, at the time periods, or at the intersections where you will see a high amount of pedestrian delay, there is more likely chance of pedestrian violating the signal. And lastly, using this research, using this project, we were able to provide a network-wide model for estimating pedestrian delay. Now, let me summarize all these projects and let me describe the project takeaways. First of all, using all the components, combining and looking at individual component of this study, we understand the impact of speed feedback signs along traditional corridors or conventional corridors. Secondly, with the second component of this research, we understand the impact of signal retiming and coordination on transit signal priority, which was used in a connected corridor. Finally, the other component, the other key learning of this project was the feasibility of using controller event-based traffic data for estimating multimodal signal performance, which for this study was pedestrian delay. And what were the broader impacts? What were the impacts of this research study? First, we were able to improve corridor safety by proposing an innovative speed management strategies. Second, we improved corridor mobility by proposing signal timing practices, an innovative signal timing practice. We, based on the model, based on the multimodal model that we developed, and based on the results, DOTs can encourage the use of eco-friendly mode choice on the corridors, which would be walking for this case study. Encourage more people to walk and bike. And one interesting and exciting outcome of this study, which I really enjoyed during this working on this project, was triple university collaboration. I get to know what other universities are doing and what other DOTs and what other cities are more focused on and is more important for them. And finally, we had university public agency collaboration, which I would like to thank again our agency collaboration, Utah DOT and Pima County Departments of Transportation. With that, please let me know if you have any questions, any specific questions for any part of this study. We would be more than happy to answer. Thank you.
Well, yeah, thank you all. Yeah, I'd like to just recognize how great it is to have a collaboration between the 3 universities on this project. For the audience now, we're going to do a Q&A. Please submit your questions through the Q&A feature. We have had a couple of questions come in, and I don't know, Abul Faz, if you want to sort of cover that one that was on the INREX you talked about.
Mm-hmm. So thank you. I tried to answer 3 of the questions here, but to be more specifically, the one that you asked was that whether we use other third-party data sources to evaluate the impact of speeding on those intersections. At the moment, for this study, we only look at the disaggregated data that we collected using the tubes, but definitely using the prop-based data such as INIX, we are also able to understand whether any specific change on any specific locations was seen or not. So that's what I meant for my for the answer. And I see another one. Does the speed feedback science research method address whether the measured speed reduction will be lasting over a long period? So this one, again, I answered this one. For this study, we looked at a short-term effect of a speed feedback science. We didn't look at long-term, but this is a great idea. And I've seen other papers that looked at the long-term effect of a speed feedback science. And you are correct. When people are used to one speed management strategies, they might get used to it, so they don't reduce their speed as much as the first week or the first 2 weeks of installing that enforcement. However, for this study, we only looked at the spatial effectiveness of speed feedback science in short term.
Great. There is one other question I see about whether the model considers disability to set pedestrian speed.
And let me see it.
It's in the chat.
Okay, so can you repeat? Sorry, I didn't catch you.
Yeah, we have a question about whether the model considers disability to set pedestrian speed.
No, for this, for the estimation, pedestrian estimation model that we developed, we only used high resolution event-based data that we collected at each intersection. So the input of the model was cycle lengths, traffic flow, and amount of green time. So we actually didn't have the data to look at pedestrian speed, but that would be a great suggestion.
Okay, anyone else any of our other presenters wanna give a little, anything missing from the presentation you'd like to add now or clarify?
Yeah, I thought Apple did a great job explaining everything, and I do appreciate everyone's support. This effort is not easy because it's we have different DOTs involved, and also thanks a lot for NITC support. So on the data collection was not easy. A lot of things actually mentioned by Apple sounds easy, but actually the data collection process was more. There are many challenges we faced, but luckily we were able to deal with all the challenges. So yeah, so a lot of details. I encourage the audience, feel free to reach out to us. We have a lot of detail where we have to share. I think it's a great team effort. I really appreciate. I've been working with a great team here.
And is there any sort of suggestion for organizations in order to prioritize different streets to overcome the if they're limited funds, limited ability to put in the speed feedback signs?
Apple?
So great question. Based on what we studied, we solely try to take advantages of the benefits of each of these strategies. For example, if there is a DOT or if there is a cities that does not have enough resources for law enforcement, using the outcome of this study, they can mix their law enforcement with the available speed management strategies in their city. So that's why we said, let's use periodic law enforcement to avoid that case. So to answer your question, yes, the other approach, if there is not enough fund to buy speed feedback signs, potentially they can use periodic law enforcement as an effective way for reducing the speed. The results of this study showed that vehicles will slow down after periodic law enforcement, but they will again regain their speed. So that if that's what cities are looking for.
And Brendan, this one thing I want to mention is that we actually did another study, which not included here, is actually they are like third-party data. They are actually quite useful to do a network screening for speeding issues. So we don't have much time to talk about that issue here, but I'm pretty sure a lot of cities, they don't have a lot of resources to do this type of study. They probably can take advantage of the third-party data. All these names. You can use the third-party data to do the network evaluation, and they can identify the hotspots for eliminating these speeding issues. Yeah, that's some idea to throw out for everyone to think about it.
Great. We have a specific question about the sort of data system architecture you used for the traffic speed data.
Thank you. Great question. As we discussed during the presentation, for each locations we installed tubes. These tubes were dual tubes, 3 locations for each side. So we were able to get all the vehicles passing these locations, their speed, their volume, their speed, their classification, and the time the vehicles passed. Then we aggregated all this information in our programming language, and that's where our results came out.
And in case they are told, this attendee was asking the data structure, it's just all the third-party data are stored in the relational database. That's a data structure we use. That's in our database. Yeah, so the data coming every minute. So we have the large amount of data we can use for our study site. Yeah, thanks to ADA support, we do get credit to ADA. So thank you.
And also one additional thing is that I believe NITC already have all the publication, but each of these sections of this presentation, they have corresponding publication. So it would be great if any additional details is I missed during the presentation, you can just take a quick look at the publication product of this project as well.
Great. So let's just, I guess, touch on where this goes next and what you see in the next sort of 5-10 years of the research around the traffic, the speed traffic sensor signals.
Yeah, I think I want to give Dr. Yan some opportunity to talk because it's not our work. So Utah, they did a great job, and also Srisha helped us with a lot of pedestrian delay research. So Terry, do you want to say something?
Yes, sure. So we actually we have been focusing on this connected vehicle data analysis, and also we got some continuous project to support the effort to work with UDOT to implement the connected automated vehicles on the corridor to collect some additional data. And one of the interesting ongoing projects funded by DOE is we're going to use the other sensor technology, such as the camera sensors, to detect the data from the regular vehicles. So then we can combine the data with the connected vehicle data. And also UDOT is working with Panasonic company to try to integrate the connected vehicle application with different scenarios. So for example, we have been discussing on how to use the road weather information and also the infrared camera to detect the hazards in winter season. For example, when we have ice or snow on the pavement, the vehicle the friction factor between the vehicle tires and pavement will be reduced, and the road become really slippery, and then we can do the detection, then send the information to the connected vehicles. So we do have a lot of ongoing efforts to continue this study.
Great. We do have a question that's I guess an offshoot of this study and may not be part of what you're working on, but there's a question in the chat about how this sort of decision-making and data-driven can be applied to predicting road accidents. Does anyone want to sort of talk about that? I know this was more about pedestrians.
Avo, do you want to talk about this?
Thank you. So first of all, I don't think we can predict the road accidents. Maybe we can predict the risk, or we can say this type of decision making, this type of speed might end up for a risky behavior, but we are not able to actually predict the accidents. But there has been a lot of studies saying that, okay, if there is a location of the roadways, or if there is a place that drivers are behaving with a lower speed, or the variance of the speed is lower than this, or you see a spike in the variance of the speed, there might be some warnings of potential risk happening. So using the variable speed, variable sign, VSL sign, they are able to inform the drivers to make their decision correctly in a way to avoid that type of conditions.
Great. Yeah. So let's wrap it up. Is there anything anyone like to add? Okay. Just want to thank you all for presenting today. We really appreciate it. I know this was a large panel for us. And we have another webinar coming up in October. So please sign up for that. And I'll just thank all the attendees, and yeah, have a nice day. Thank you. Bye.
Thank you.
Thank you.
Thank you. Bye.
Thank you.